So, I'll talk about odds ratio. As before, my notes on this will be on the website with these, which you can get from your timetable, but also you can go directly to my website. Okay, so the odds ratio is specifically designed to answer questions where the outcome is a yes or no. And it's also specifically designed for the situation where the input is, well, it could be anything technically, but the traditional kind of odds ratio is when the input is also a yes or no, or a category A or B, something like that. So it has to be two categories to two categories. That's what the odds ratio is designed to deal with. And it does also have to be that this category has to define completely separate groups. One group that are all A and one group that are all B. And that's the same situation in which you do the chi-squared test. But the odds ratio is not designed to answer a yes or no question of is there a relationship. The odds ratio is designed to describe how strong that relationship is. Okay, so it's a describe question. It's designed to say how strong is the relationship between this and that. So how strong is the relationship between gender and participating in volunteer work? How strong is the relationship between treatment and whether someone develops heart attack? How strong is the relationship between whether someone had the fried chicken and whether they developed gastro? Okay, so that's what the odds ratio is designed to do. It's talking about the strength of the relationship. It doesn't answer the yes or no question of whether there's a relationship at all. It just talks about the strength of the relationship. And the way that it talks about the strength of the relationship is it compares the likelihood of someone in category A and someone in category B of having a yes outcome. Okay, I'm just going to make sure I'm saying the things I'm supposed to on my notes. So you have to compare one category to the other. It doesn't matter which way around you do it, but usually there's a logical way of doing it. So usually it's the person who's exposed, the people who are exposed to some risk factor compared to the people who aren't. So for example, having the fried chicken compared to the people who didn't. And it's the odds. The odds of picking, I'm going to need more space than that. Sorry about that. Odds of picking someone in category B with a yes out of the compared to odds of picking someone in category A with a yes. I'll do an example of how that's done if you're interested, because odds is not an ordinary way of calculating probability. Okay, so the odds ratio is if you have something where there's A and B and yeses and nos, and maybe there were 50 people with A and 50 people with B, and within A there were 20 that came out yes and 30 that came out no, and maybe this time it's 60 that came out yes. That's bigger than 50. I'm thinking percentages, and 10, much better. Then your odds ratio is the odds of picking someone in category, so this is the odds ratio comparing B to A. So the odds of picking someone in category B with a yes. So let's see, we've got a 40 out of 50 chance of picking someone in category B with a yes, but odds is actually not the number out of the total, it's the number with yes compared to the number with no. So odds for yes in category B is 40 out of 10 compared to 10. Okay, there's 40 with compared to 10 without. And the odds for yes in category A is 20 out of 30. And so the odds ratio 40 out is that, whatever that works out to be. It turns out that if you do the maths, because when you divide by fractions, you flip the bottom fraction upside down and multiply instead, it turns out that it comes to the same answer as this times this divided by this times this. So if you start with the yes in the category that's going to be the one that's being compared against, if you want the odds comparing B to A, you start in B, and that's this one, those times together divided by that times together, and that's the odds ratio, which in this case is coming out to an answer of 6. Yes. So that's telling me that people in category B, well, I'm 6 times more likely to pick someone with a yes in category B than I am in category A. I say it precisely that way because it's not technically saying people in category B are 6 times more likely to have yes than people in category A. Well, it's more likely they have yes now. Okay? So people in category B are 6 times more likely to have yes now than people in category A, but you cannot say people in category, if this was a disease, if yes was a disease, so maybe it's getting gastro, I could not say people in category B are 6 times more likely to get gastro than people in category A, because that's talking about the future, and the odds ratio only talks about the present. It talks about who has or does not have it now, not who will get or will not get it in the future. Yes?
Can you explain the difference between saying 6 times as likely and 6 times more likely?
6 times as likely and 6 times more likely is the same. At least it is for me. If someone else has told you that it's different, grammatically it's the same. So if someone tells you that it's different, use whatever crazy rule they have for telling the difference. But I can't tell you why they think that. I'm sorry. But I would, just to be safe, 6 times more likely. Yes, in my head they're the same. I could be not understanding English grammar well enough, but it could be that 6 times more likely is actually not grammatical at all to say. Yeah, because 6 times, I think I have it. 6, no. 6 times more could mean any number of things. So I'm just going to leave it at that. A risk ratio, by the way, is concerned about the future. It's about the chances of contracting something in the future, and it's calculated differently just while I'm at it. In a risk ratio, you're in the odds ratio, in the situation where you just have a group of people now and they have or do not have the yes or the no. A risk ratio, you had a group of people and everybody had no to begin with, and you watch to see who comes into the yes category later. And so risk ratio is totally different because it's about the future. And so you have category A, which might have a certain number of people and everybody's no to begin with. And then later on, maybe 20 are yes. And category B, their 50 is all no, and then later on 40 are yes. Okay? It's the same situation at the end that we have before, but we're talking literally about the risk of contracting yes. It's this disease called yes, right? So contracting yes disease, and so it's actually 20 out of 50. It's not comparing who has to who hasn't, it's comparing who has now to who didn't before. So it's actually, the risk in category A is 20 out of 50, and the risk in category B is 40 out of 50, and so the risk ratio B to A is 40 out of 50 compared to 20 out of 50. Whoops, sorry. So note that if they had different sized groups, it would come out to whatever it comes out to. It would be, these numbers here would be different. At the moment, since the groups are the same, it's just 40 compared to 20, which is 2. But if the groups were different sizes, it might be different. So this is saying people in category B are twice as likely as people in category A to eventually have yes. That's the difference between risk ratio and odds ratio. It took me years to figure that out. If it doesn't match with what you're being told elsewhere, use whatever they've said. But as far as I know, that's what it is. If you want to know more, Medical Statistics at a Glance is the most excellent book which talks about these things. And this is what's used in epidemiology. So if you look up epidemiology online, it might give you some philosophies about how the whole of this stuff works. Okay, but the final point I'm going to make back here on this page is that if the odds ratio comes out to 1, same likelihood in both. Okay? And that's important because in other situations the number coming out to 0 means the same likelihood. Not the same likelihood, means that there's no difference. But with odds ratio, if it comes out to 1, this means there's no difference because you've done a division instead of a subtraction. So that's just important to note. So in other situations you're looking for a 0, and in odds ratio you're looking for a 1, or at least not being 1 is the key. Okay, so the other thing I wanted to talk about was logistic regression. On the list here it talks about linear regression and correlation, but I talked about them in quite a bit of depth in the regression lecture, so I'm going to leave them, but I am going to talk about logistic regression. So logistic regression is a special kind of regression which is designed to have yes or no outcomes. Okay, you've got a yes or no outcome, and you want to know whether one or possibly more things affect this outcome. And the things that affect it are usually numerical variables. But they don't have to be, they could be categories as well. Okay, it doesn't matter how many there are, but the simplest kind of logistic regression is that kind, that just has a numerical explanatory variable affecting a categorical outcome. And the categorical outcome is a yes or no, and you'll usually inside the computer declare the yes to be 1 and the no to be 0. Okay, so that's what logistic regression is for. And what it does is it finds a formula for how likely it is to find someone with a yes depending on these variables here. So you'll have whatever this is and whatever this is, and you'll chuck them in a formula and it'll produce a probability for coming up yes. Okay, that's what the logistic regression will do. Technically it doesn't produce a probability, it produces an odds. Actually it produces an odds ratio. So it compares everything to some sort of base case. So for example, this might be age, and it might compare everybody to age 15, and this might be gender, and it'll compare everyone to maybe male. And so your base case, everything will be reported as relative to 15 male. Okay, so that's what logistic regression is for. And it's a very special kind of regression because ordinary regression is a very fabulous formula that tells you, based on your data, what the equation should be that connects those variables. But logistic regression has to be done with what they call maximum likelihood estimation, which literally the computer tries a whole lot of options and picks the ones that's the best. Okay? And that's why logistic regression hasn't been very popular until today, as in the last 50 years, maybe less, last 30 years, because computers just haven't been able to do it up until now. Okay, so just let me write that down. You get a formula for the odds of yes based on the explanatory variables. That's the goal. Okay? Now, as I said I think back in the regression topic, technically that's a predict goal. We're trying to predict what the probability will be based on the input. But as with all other things, if what you want to know is there a relationship, you can also do logistic regression. And I should also say that if you have this situation and you want to know is there a relationship, you can pretend the arrow is pointing the other way and do a t-test instead, and that will answer the same question and it will give you the same p-value. So just a second, if you want to know is there a relationship for this situation where it's a number affecting a category, can think of it this way instead and do an unpaired t-test. And this is why I write my handout later with much better handwriting than this. So if you want to know is there a relationship, relationships don't go in a particular direction. Like mathematically, if things are related this way round, then they're related this way round as well. Okay, so there's no particular reason if all you want to know if is there a relationship to have the arrow pointing in one direction or the other, and so therefore a t-test will do a perfectly good job of telling you if there's a relationship. If you want to find the formula that says, you know, for what this level of the explanatory variable, what's the outcome, then you need logistic regression. And if you want to do this question when there's multiple variables involved, then you have to do logistic regression. Okay? Right. So, let me just talk a little bit about that and then I'll switch over to the other thing. So, in ordinary regression, your number that comes out is done through some sort of formula that looks like this. You have your number that comes out is some number plus some number times the number that went in. And that's how it normally looks. Please make sure there's space here if you're going to write this down now. Okay? But the thing is that the outcome's just yes or no, right? There cannot be a formula for it. It'll either be 0 or it'll be 1 if you turn it into a number. And so we need a better thing, which is the probability of coming up yes. Do not write this down yet because I'm going to change it. So the probability of y is going to be based on some formula, but let's have a look at this. Probability of yes is a number that goes from 0 to 1. Okay, probabilities are percentages, they're out of 100%, and statisticians don't like writing percentages, so they write them as decimals. So it's between 0 and 1, and this means no chance of getting a yes. This means it's sure to get a yes, and this is equal chance here. Okay? But the problem with regression is that it can spit out any numbers. It could give me a minus 0.7 or a 1.8, and that's not useful. What does it mean to have a 180% chance of something? That's ridiculous. And so what we do is we turn it into odds. So odds is comparing the chance of yes with the chance to no, and the odds is much better because it always comes out to a number like this. It'll be 0. If there's no chance of yes, the odds will be 0. If it's 50-50, then it's 50 for yes, 50 for no. When you divide them, you get a 1. Okay, equal chances. And if yes is completely certain, you'll get an infinite odds. Okay? So sure is out there somewhere. And that's awesome, because now we have more options. We could get 1.8 now, because that's great. 1.8 just means that you're 80% as more. That's it there. Right. If the odds ratio comes out as 1.8, that's 100% plus an extra 80%, right? If you said 80% as likely, that would mean that the likelihood would be 80% of what it was before, so it would be smaller. But if you said 80% more likely, then it means it's actually 180%. That's the difference. Right. So if you turn your if you turn your 1.6 into 160% and then turn that into 60%, then you have to say 60% more. If you just say 1.6, you can say 1.6 times as, yeah. But you won't use, because it's a percentage, you won't use times, you won't say 60% times, you'll just say 60% more. Right, now I understand. Okay, and then there's still a problem because what if it comes out as minus 0.3? So we're going to do the log of the odds. And then what that's going to be is that the log of 1 is 0, and you'll get plus infinity when it's sure, and minus infinity when there's no chance. And that's great because mathematically now we can get any possible number, positive or negative, and it has the convenient property of 0, meaning no difference, okay, meaning equal chance. And so that's great. So what we actually want is the log of the odds of y comes out of this formula. And that's what logistic regression is doing, and that's why it's doing it that way. And also because logarithms do some nice things to the maths when the computer's trying to figure it out. And this is why when you calculate confidence intervals for odds ratios, they end up with all these logs and things in there, because those confidence intervals are actually calculated using logistic regression. Yes. So when you look up a paper and it has like this outcome is being predicted by, you know, age, and then there's covariates of gender and various other things, and they adjust for those, they can't get confidence intervals because there's so many things involved. What they're really doing is logistic regression, and the confidence intervals is coming out of that whole process. And because the logistic regression uses the log of the odds, that's where all the logs and exponentials come from when you do confidence intervals for odds ratios. Right. Before I stop recording, any questions? Cool. I will make sure my notes reflect the extra stuff I've got here. The notes that are currently there have last year's version for the odds ratio and the logistic regression, but I've added a bit of extra. So I'll change them within the next couple of days, and you'll be able to download the new one.